Programming Throwdown, Episode 64, Cryptography. Take it away, Jason.
I actually want to talk about interns and how important that is, understanding how the whole internship process works and implications there. I'll kind of walk through sort of the whole internship kind of cycle. Basically, typically you interview, you're typically in college. You could be undergrad, graduate student, doctoral student. You will interview around like December, January-ish. So you'll apply around, I guess, November, December. But definitely check with whatever company you're interested in because it varies. And then, you'll do typically a couple of phone interviews. And then if you're accepted, you'll sort of formally accept the offer, and then you'll be committed to spending your summer at whatever company you apply to. It's pretty cool. I think it's very sort of loose. Like, I've seen really amazing, super exciting internships where you're basically a full-time engineer. You have a ton of responsibility, you have a lot of help, and some amazing work comes out of it. Now, I've seen internships that, didn't go as well. So it's, because it's such a short time, it's, there's going to be high variance, right? But one really key thing is it's super, super important to do an internship if you want to go into industry. It raises your chances of getting a job significantly. There are times in companies I've worked at where there have been hiring freezes and they still will hire people who are interns, even through the hiring freeze. So it's really important. I personally haven't done an internship, but I have over the years kind of mentored interns. And that's another part of it is you'll get paired up with a mentor who is kind of responsible, kind of like a manager. And they're responsible for helping you, making sure that, if you're blocked on something, that they can get you unblocked. Of course, this is really important for an internship where you only have, a couple of months. And I think, Patrick, you actually did an internship, right?
I did. I interned at a company that I ended up going to work for once I graduated, because that's like a thing companies try to do is for the interns that do, well, they sort of already learned about them. They've spent some money training them. And so they try to be generous in giving them offers to come work there. The other thing I don't think you mentioned is that being in engineering, specifically computer science, I've never heard of an internship that was not paid.
Oh, that's a good point.
So in other sort of disciplines, it's very common to have internships that are not paid, that you sort of are expected to give work away in exchange for the experience. But all of the programming internships I know of are paid, and they're actually paid pretty well, like much better than the sort of other summer jobs I took that were internships.
Yeah, absolutely. Yeah, internships are paid if you do some type of engineering role. I have a friend who's in biology, and their internships are not paid. So it's kind of and it's still very common to do internships even in that field. So we're super lucky to be in a field where they pay interns. I think it's a great experience. The other part of it is, there's definitely a big rift, I think, between academia and industry right now. If you're in academia, you probably are being taught about linked lists and about hash tables and things like that, which are, super important. And then typically you'll have maybe one software engineering class, but that class will, at least at my university, was just woefully out of date. It's like UML diagrams or something, which was like, popular in the 90s or something. And so, getting an internship gives you just like an extraordinary experience that's very hard to sort of replicate in school. It also will help your interview skills. It'll look good on your resume and all of that. So, definitely check it out. If it's not on your radar, it would be good to just, check out pick your favorite companies, and see sort of what they have to offer on the internship side. The other part of it is it's not as big a risk for a company. So, depending on state to state, but in general, if a company hires you, especially if you're there for more than 3 months, there's definitely, it's hard to get rid of people. Like, to say, like, perfectly honestly, it's hard, very hard to fire people in general. And I think in Europe, it's even harder, right? And so what that means is people are going to be risk adverse, right? They're going to take every possible precaution, not to be put into an awkward position, right? And if you've done an internship, that gives extraordinary signal to that company. I mean, so if the choice is between you and somebody else who, as far as the interview goes, is, maybe even a little better, did a little better in the interview, but you're sort of a sure thing and they're just high variance because they didn't do an internship, I think that will, factor in, right? On the flip side, I don't think internships like matter to other companies to the degree that they're worth getting. So in other words, like, don't do an internship at a company that you would never work for just to do an internship. I feel like that's a waste. I think you would be better off like taking a Coursera course or something and putting that on your resume.
I disagree.
Really? Well, I'd like to hear your opinion.
So I think it is absolutely true that doing an internship doesn't matter nearly as much to another company. But even if they discount your work experience there, or sort of, kind of pretend that it isn't there, I don't think it's a negative, right? They're not going to be like, oh, you did an internship at another company, we don't want you here. And I think there's a bunch of positives to it. One, from your end, you're going to be able to have gotten a little more experience in the process of doing that you can talk about during your interview, that you will help you in your last. So typically, sometimes internships happen at the end of your schooling, but often they happen sort of before your final year or before your final 2 years. And then it sort of gives you an opportunity to shape that last year or 2 years to what you learned about during your internship, or what you sort of learned about the real world. I guess that sounds bad to say, but non-academia, it's sort of what Jason was alluding to. And I think all of those things actually help you. When you go to interview, people can tell, oh, this person is sort of ready. Like, they've sat here. They're not going to ask, you're not going to have to ask questions like, what is it like to be a programmer? Like, what do you do all day? Those might be questions that come from someone who's not. And I think all of that sort of comes through in sort of the disposition of a person, even during interviewing, if they've done an internship before. Taking a Coursera course is great. I don't know how to really compare and contrast those, but I think there is value. I mean, at some point, taking it in sort of a field of computer science you're not interested in going into, and at a company that's not very reputable or whatever, at least you still get paid. So there's that, and like making money is sort of good to like help you get through college.
That's true.
Because I was sort of broke in college.
Yeah, same here.
So that was really nice. And I see what you're saying,
fair.
But I wouldn't say it's a case-by-case basis. You sort of have to make a decision. But I do actually think there's enormous value. In my time when I was back at college after doing an internship, it gave me, I feel, a much different view on my professors and what they were saying, where it allowed me to sort of apply what was being said a little more intelligently and sort of focus on the parts that I really wanted to make sure I knew. And sort of, in my mind, since I wasn't going in academia, allowed me to discount some of the stuff that I realized was sort of no longer applicable to kind of the stuff I would need when I first came out of the gate.
It makes sense. I mean, I think I'm definitely kind of like a bookworm. So, it's a bit of like, I think my values coming out. But yeah, I think, so maybe, one thing I think we both agree on is definitely, take the time to like, take the time to pick a company for your internship that you would want to work for. Like that, like interning, gives you a huge leg up at that company that you interned at. And so don't kind of like waste that. Like if you That's really want to work at, General Electric or something, then do an internship there. And what that means is kind of really doing research kind of early on the companies. and where you want to work. But yeah, I see your point that there's definitely, you get a ton of experience either way. And I think you're right that even if, let's say you do internship at GE and then you go interview somewhere else and they don't really know much about GE or care or something like that, you're still going to have experience that's going to show that you wouldn't have had otherwise. All right. Time for news. So, so this is one of these things that's almost like scary to even bring up. But we have to talk about it.
They're listening.
Yeah, that's right. So I'm sure everyone's seen by now this whole Vault 7 WikiLeaks thing. Basically, and I guess, I don't know if it's, I don't know how much of it has been sort of proven or not. I haven't been following it too closely, I have to admit. But basically, WikiLeaks released a bunch of documents from the CIA. And among other things, it says that if you had a Samsung smart TV, that they had some sort of hack where from your Wi-Fi router, they could like get into your Wi-Fi router, and then from there they could get into your TV, and they could actually turn on the microphone just at will. So, and so presumably they were just turning on the microphone, they were collecting all of this audio, and then they were shipping it to Germany, because I guess the idea was that if they get caught, then they can like say that it was the Germans who were doing it. So it's sort of like a way to cover their tracks. But I guess apparently there's like, and again, this is all from the WikiLeaks. I don't know if any of it is true. I have no idea, right? But according to this report, there's a bunch of Americans, living in Europe doing like all this analysis on all of this illegally collected data. Presumably they're like looking for people who are like speaking a certain way or saying dangerous things. I don't know. But the whole thing is crazy. And it goes way beyond Samsung TVs. It's like iPhones. There's like 0-day exploits for iPhones that they had that they weren't giving to anyone so that they could like survey people on their iPhone. My ignorance of the topic is kind of showing through. I saw the initial news article, and that's kind of what I've linked here. But there's a ton of information. If you're at work, don't download this at work. like WikiLeaks has this zip with like all this data. You probably don't want this on your work computer. That's one of these things. It's like, you don't really think about, because it's not really illegal. It's not like pornography or something like that. But I don't know. Maybe it's just me being paranoid, but I feel like this is probably not something that you want on your work computer. But yeah, when you have time, at least read the articles. It's fascinating. Even if it's not true, just the whole story just seems completely plausible. And, it's an amazing read. There's also tools. You can actually download these like Windows and Linux tools that supposedly let you, sniff ports or something. I don't know too much about it, but they have the source code and everything, which is kind of wild.
Yeah, as you said, even if it is sort of fabricated that it was the CIA or the CIA was behind that, or not fabricated, but whatever, miscommunicated, misunderstood, who knows. Even if that part isn't correct, then it gets people thinking about all these sort of Internet of Things, the smart TVs, the smart toasters, the smart microwave. Anytime they put a microphone on there to listen to you for some reason, even a sort of legitimate reason, then someone could figure out a way to tap into that and gather that data, even if the company is complicit or non-complicit with that.
Yeah, I had friends, coworkers who, would put tape over their laptop camera and tape over their microphone. And I kind of I didn't think they were kind of like tinfoil hat wearers or something like that. I feel like, makes sense. Maybe you have an accident, you turn it on when you're not supposed to, or like, maybe you actually download a virus, like you install some program that's malware or something, right? But I thought the idea of like, oh, the government has some 0-day exploit in the OS and they could just, turn on your camera at will. I thought that was kind of like a stretch, like kind of out there. But yeah, after this report, I believe it. I mean, I still haven't taped over my camera. Maybe I just don't care if someone's watching me. But yeah, I totally think that I could be watched at any time, which is kind of strange. I don't know. Oh, go ahead.
I'm sorry. This sounds really silly, but you said put tape over the camera, and I have actually done that a couple times because we used to have a video conferencing tool that had the option of having video on or off, and sometimes you would sort of not be paying attention or not have the configuration right, and it would turn on the video by default, and then until you sort of realized it and turned it off, people would see you sort of, not doing something weird. It just would sort of catch you off guard. And so I actually did have something over it.
When I don't think people are watching, I like scratch my face. Like, like you just do these like habitual things. And it's kind of embarrassing, right?
And so I put electrical tape over it, like some opaque tape that you couldn't see through, because I thought that made sense. And then someone the other day had cellophane tape, like clear Scotch tape, it's like sort of hazy over theirs. And I didn't get it at first. And then I realized and then asked them to confirm that this was why. Is sort of, one, it wasn't as tacky because it wasn't as obvious when you looked at it. Also, some of the computers use the camera to do ambient light sensing, or in that area to do ambient light sensing. And if you tape over it with tape, you ruin that, or electrical tape or a piece of paper. But if you put the cellophane tape, it can still sense the light, but everything is sort of too blurry.
Right. That makes sense.
And I was like, oh, I guess that seems silly, but to me, I was just like, wow, that's really smart.
Yeah, totally.
So if you don't want to go all the way and use...
We're going to see a lot of this now, I think. Like we're going to see a whole market of smartphone cases that can, cover and uncover the camera. I just feel like this is like a thing that's going to happen.
I feel the opposite. I feel like people are scarily desensitized and not caring about this.
Well, I mean, you'd be right in the case of me. I don't really care enough, and maybe that's a scary thing. But no, I think that, even if 1% of the people care enough, that's enough of a market for someone to make a case with a lid or something.
I'm not denying cases will be made. I'm just denying that they're going to get used.
Yeah, I agree with that.
Well, my news article is about SHA-1 collision. So I guess this is from Google. Announced I guess they were trying to call it something cool. They called it Shattered. So they named the bug. Right. It's not really a bug, but there's a tradition of naming, I guess, exploits and bugs. So they named it Shattered. But what it really is SHA-1, which is a way of hashing the data, which means you sort of take a document or a bit of data and you run it byte by byte or sets of bytes by sets of bytes through an algorithm, and you get it's called a hash back. It's some representation of that data, so that if you make any change to the data, it is statistically improbable that the hash is the same for two different inputs. Now, of course, if your hash is smaller than your input, it's always possible, right? So if you have input that's 256 bytes and you use only 1 byte hash, then of course there's always a chance that they'll have a collision. But with a big enough hash, the chance of collision goes down dramatically, right? You could imagine, for 256, a 1 byte number, a 256 combinations, that any two documents have, what would that be? 1 in 256 chance of collision. And then there's sort of what do they call it? The birthday problem, where there's sort of a little bit of unintuitiveness if you're not used to dealing with it, where your chance of collision goes up more quickly than you would otherwise sort of think. But even with that with the longer hashes, it sort of was for a long time unreasonable to expect that there would be a collision, which is two different inputs causing the same result. And the reason why that's bad is if you imagine someone is like when you see the sort of hash codes for downloads when you download, especially like security tools like an SSH tool, and you'll see like, oh, here's the hash, and you're supposed to hash it on your computer to make sure that the thing you download matches the thing the author intended to. And so that way nobody's changed it. And with a collision, they could give you a virus instead of an SSH tool. And so what Google did here was created 2 different PDFs. And I haven't actually opened the PDFs, but I read that they were essentially 2 images. So on the first PDF, there's an image. On the second PDF, there's a completely different image. They don't resemble each other at all. But if you run them through this SHA-1 algorithm for generating a hash, the hash will be identical. And what that means,
they did it on purpose.
Right. They found 2 different documents that collided.
Right. And they can, and the important thing is that because you could generate just random data and hash it, and then generate more random data and hash it, and eventually you'll get a collision, right? But in this case, they can actually manipulate the collision. So in other words, like they can get something, not just random, but something they want to collide with something else. And that's where it gets kind of dangerous, right? And a funny kind of side note on this, they put into Chrome a unit test where there was a collision. And so just as part of Chromium, and I guess Chromium, like, I actually don't know why they put it as a unit test. Maybe it's just to remind people never to use SHA-1. But as soon as they put in that unit test, and they put in those 2 PDF files, it actually broke a Git. Like, it literally broke the repository, and the Chromium repository was down for like almost a week because Git saw these 2 files with the same SHA-1 and just had a heart attack.
Yeah, so this is dangerous. They have on the website, we'll link it in the show notes. They have a list of how much effort they put into getting this collision. But if you sort of look through the trend of these things, whenever sort of algorithm like this is sort of proven to be vulnerable. So for a long time, people have said, don't use SHA-1 because it's close to being vulnerable. But sort of no one had actually proven it to be, like proven here definitively we have a collision. And now that they have, it'll only probably be a matter of months, maybe a year or whatever, before the computation falls even cheaper, and maybe a couple years or whatever. It just means that basically any time now you should expect this to become commonplace where people are able to create collisions. So using SHA-1 for something security related has just become much more dangerous.
Yeah, it's kind of like WEP. Like WEP, someone hacked it, it was a big deal. And then like less than a year later, there was WEP attack. Like you could just sudo apt-get install WEP attack and then get any WEP password you want. And it's just completely democratized.
Yeah. All right. Well, time for Book of the Show.
Book of the Show. My book of the show is my first audiobook from Audible. As I said last show, I was getting kind of eye strain from too much smartphone, too much computer, and I decided to get an Audible account and listen to audiobooks and wear one of those opaque masks when I'm on the bus. And I did that, and it feels really good. And so my first audiobook was Scott Adams, who's the creator of Dilbert. He wrote a book called How to Fail at Almost Everything and Still Win Big, The Story of My Life. Or kind of the story of my life. And it's interesting. I mean, it definitely, it reads kind of like a self-help kind of manual. I mean, it is a self-help kind of manual. He does definitely talk about his life. And maybe it's just because I'm getting, to the end of it. But I really was interested in the beginning. And it is all about his life, his trials, his tribulations, sort of his mentality, sort of what got him through the different hard parts in his life, etc. But then the second half of the book is all about, I guess the title of the book, which is all about how the audience can fail at everything and still win big. And that's the part that, it's definitely interesting, but it's actually, maybe what it is honestly, I have a lot of the same mentality as Scott Adams. And so for this reason, it's like I'm just hearing myself say things like nothing seems that interesting to me because I already think sort of the same way. And so for that reason, maybe, you know, someone else could get more out of it, or maybe it's a contentious book to other people. But I found that part like a little boring for me. But the first part is just super interesting about his life. I always kind of wondered, you know, people who write comics, sort of like what's kind of their persona. And you definitely get a long glimpse into that. So yeah, I totally recommend it. It is a great listen, and I'm really happy with my purchase.
I actually normally have sci-fi recommendations, except that I'm in the middle of a really long book. And so I try to not do my recommendations until I finish with the book, although I know I have in the past. And so I'm withholding that one until next episode, and I'll be finished with that book. So instead, I don't think I've ever covered this, but I really like Make Magazine. And Make Magazine has been around, I don't even know how long now, for quite a while.
A long time.
And I've always sort of, when I've gone to the bookstore and seen a copy of it that I was like particularly interested in, I would pick it up, or I would sort of follow their blog online. But I finally got a subscription to it, and, you know, just been receiving in the mail, which I really like, just sort of getting it by default and then reading through it whether I sort of thought I would or not. And, which is weird because I guess I don't normally read that many in-print books or magazines. But I'm enjoying this one. And Make Magazine caters to what I guess they sort of helped create the name for, the maker crowd, the maker movement, which is to sort of say people who enjoy making things with their hands, not just buying things off the shelf. So putting together electrical kits or making circuits, 3D printing, making their own quadcopters, just the whole gamut of sort of mixing art and technology and coding and electronics. And they cover all of those things. And the magazine itself is just sort of, I think, really well done. I don't often do projects that I find in there, but it's still inspiring, even if I don't, to sort of read through it and see the way they've described something and the cool stories they have in there and the tools they recommend, and learning about sort of, you know, hey, what are people doing with Arduinos these days, or with wireless sort of little PCBs. And so if you've not checked it out, I'm sure most people have probably heard about it, but if not, and you feel like you're into that kind of do-it-yourself, crafting, trying new things, experimenting, definitely check it out.
Cool. So this is, I guess, can you get an electronic version, or it's only in
I'm
print?
sure. So I have the print version. I guess I just think it's a really well-done print magazine, but I know they also do have a digital version.
Cool. Very cool. Yeah, so you can definitely get, one of Patrick's mega million-hour audiobooks, or you could get the Scott Adams audiobook, which is 8 hours.
8 hours? That's like one day of commuting for me.
That's right.
No, that's not true.
On Audible. So you could go to audibletrial.com/programming throwdown, all one word. We have a link in the show notes, and you can get started on that. I thought it was great. It's got a pretty cool interface. Oh, one thing I noticed is the interface on Android is way better than iOS. I think it's because on iOS they can't actually sell it as an in-app purchase, because iOS, like Apple, want to take a cut. So they have to sort of get you to go to the website. But yeah, the Android version is very slick. And the Android version doesn't have the CIA spying on you, so there's that too.
Oh.
Actually, I don't even know if that's true. They're probably spying on you on both of them, but
that was horrible.
if you're not interested in Audible, or you already have an account, you can also sponsor us on Patreon. All of your donations go to help the show in some way. At the end of the year last year, we had a bit extra, so we gave away some free T-shirts. But to be a sponsor on Patreon, you go to patreon.com/programming throwdown. And we appreciate all of your donations and your support.
Yes, thank you for all the help. So I checked, my audiobook is just a little bit shy of 46 hours in length.
Wow. That's intense.
I'm very close to the end.
Oh, wow.
So,
Well, yeah, that's awesome.
okay. Anyways, that's a teaser for next time.
Nice.
People will probably go figure out what it is, and they'll be like, "Oh, I know." No, nobody cares that much. Okay. Tool of the show.
Tool of the show. My tool of the show is Tesseract. Tesseract is pretty cool. It actually was a company. Oh no, it was done by Microsoft. Then Microsoft kind of abandoned it, and Google picked it up. And it's been maintained by Google ever since. And basically, it's OCR. So it's OCR stands for optical character recognition. And so you can give it an image, and it will tell you the text in the image. Now, it's meant for books. So, you can't give it like a street corner with like a stop sign. It's not going to show you the word stop. It's meant for a book where it's, text and there's not really any background, right? With that said, though, it's extremely accurate. So you could give it, you could have a page. I don't know how it works with forms. Like it may or may not be accurate. I haven't tried that. But you could definitely give it a page from like a textbook that you've scanned, or, a letter that you've received that you've scanned. You can just take this, you can download Tesseract. You have it through a homebrew if you're a Mac user, or if you're on Linux, you have it through, apt or Yum or whatever package manager you're using. If you're on Windows, you could probably download a binary. I don't know. But you get this Tesseract binary, and it's just as simple as saying, look, Tesseract, and then the file name, and then boom, you have the text. And it even tries to use sort of it tries to be spatially aware. So if some of the text is center aligned, some of it's left aligned, it'll kind of pad with spaces. So for some things I was doing recently, I had like a bunch of images that I wanted to convert to text. And in my case, the images had a background, but I was able to sort of remove the background using some image processing. So get it to where it was just the text. And it worked great. It just dumped out all of the text I had a lot of images, thousands of images. And there was a couple of like weirdness, like, there's like maybe one or two letters is off, but, it actually uses like also the knowledge of the language. So for example, if these are English documents and you tell it English, it will, take that into account. So if it thinks the word is THIMK, but it knows that it's very close to think, which is an English word, it'll change it to think. So that fixed a lot of the errors. But yeah, if you ever need that, Tesseract is pretty cool.
Will it do, sort of like you said, scan where it is sort of aligned and flat? Will it, if you just sort of like take a picture with your cell phone, will it, kind of... I guess there's tools on your cell phone, but if you just had pictures that you had snapped with a camera or whatever, and it wasn't sort of like properly aligned and it's sort of off center and there's some background.
Oh yeah, that's not a problem.
Oh, okay.
That shouldn't be an issue. Yeah, it's just what it can't do is like a street sign or something.
Sure.
But yeah, if you have a document you've taken like, or a check or something, you've taken like a crooked picture, it shouldn't be a problem.
Cool. Mine is less useful, but maybe more fun. Is Pandemic, the board game, the app. No, the Pandemic
nice
board game made into an app for iOS and Android. I checked that it's available on both. It isn't free. Cool. I think it was at this time $2 on both. If you've never played Pandemic, the board game, I would recommend checking it out. It's very fun. If you're not into board games very much, you've probably never played a board game like this. It's what's known as a cooperative board game, which means each of the players who are playing, you can play with, I think, you can play by yourself, but you can play with, I don't remember, I think 6 people may be the limit. I'm sorry, I actually haven't played with other people, the physical board game that much.
I think it's 4, but if you have the expansion, it goes up to 6, if I remember correctly.
That might be what I'm thinking about. But, okay, so some number of other people, but everybody is sort of on the same side, on the same team. In this case, you're a set of researchers and scientists that are trying to cure viruses that are infecting the world. And there are sort of rules for moving the game along where the viruses obey sort of certain rules of logic that the game tells you how to apply in cards that are used. And by playing those cards and obeying the rules that are in the rule book during the phase of the game's turn, the virus is sort of spread throughout the world. And that spreading throughout the world, you have to combat with the other people on your team to try to rid the world of those viruses, bacteria, disease, and those pandemics. And that board game is a lot of fun. It's really highly rated. People really enjoy that game.
It's great.
The app is a really good implementation of the board game. So I actually don't get a ton of time to play this with people because I just don't tend to actually get as much time to play board games as I'd really like. But I can still enjoy the board game by playing on my iPad or my iPhone.
Can you play over the internet with friends?
I won't. This sounds. I don't want to make it sound sad or cheeky to say I don't know because I don't have friends. But I don't. I've not. I don't actually. Let me bring it up and see. I've not tried.
Well, you could just play with your Oh wait, you don't have a Facebook account. You could play with your. Oh, you don't have a Twitter account either.
I'm really bad. I don't know. I kind of enjoy. I'm not a big multiplayer game person, so I don't actually know. Oh, it's asking me other questions. I'm not sure. I'm sure the internet can tell you this answer. I did not come prepared. Sense. You've stumped me.
I would definitely, I think a game like this is kind of fun if you could play with like your family, if each of you can just play on your own phone and it just goes round robin, but it might take a long time to get through a game.
So you've played Pandemic though before, the board game?
Yeah, right.
Okay, cool. Yeah, so have you played the newer one where there's sort of like a meta game where stuff happens in between the games?
Oh, no.
So I think it's called Pandemic Legacy.
Okay. That sounds cool.
Anyways, for anyone out there who has played Pandemic and enjoyed it, there's something called Pandemic Legacy. And I've not played this before. But this sort of what happens is you play, and based on things that you choose to do or winning or losing against the viruses in the game, there's sort of envelopes and instructions that come along with the game that you open that modify the game and the game rules in sort of irreversible ways. And so cool. People don't sort of like, you won't find online exactly. I'm sure if you go digging, you can find it, but it sort of doesn't tell you what those are, but it might be something like renaming a country or adding new connections or deleting connections. I don't actually know. I've not played it, but you sort of end up physically altering the board that you have as you play these games. So you can't like go back. So by the end of playing this sequence of games, you have sort of like a customized board to your sequence.
It's almost like campaigns in D&D.
Yes. Yeah. So if you've not heard about that before, people seem to really like that. I haven't had a chance to play those because you sort of need to play it, many times through over the course of several sessions, but you kind of want to play with the same people so that you can kind of enjoy the unfolding together.
Yeah, makes sense. Super cool.
Time to talk about cryptography.
Right. Cryptography. You want to get us started?
Well, I thought I'd be a little cryptic and instead tell a story. No, okay. The thing.
Instead, instead we're going to actually encrypt this whole conversation.
So from now and for the next 10 minutes, you'll only hear static.
Yeah, it's only going to be Pig Latin.
Okay. Well, all joking aside, we're going to sort of give kind of a high-level overview of different parts of cryptography. This is a huge field from the sort of practical standpoint of how do you encrypt stuff efficiently and where does it live in your code, to the mathematical sort of proofs of robustness of various cryptography algorithms, to I know, just all sorts of things at every level. This is a very wide sweeping topic. And, there's whole professions and fields that are, sort of dedicated to working with cryptography. And we're going to just sort of give it a high level overview in the kind of different aspects and parts. And we'll probably miss a whole bunch. But the thing, cryptography is, I don't know the break down the word crypto and graphy, but what cryptography is about, I have some data and I don't want other people to know what that data is. So I have information that I want to keep secret, or I want to give it to someone else and know that only they can read it. So Jason and I can communicate and only Jason and I know what's being said so that no one else can be a part of it, or only the people we choose to be part of it are part of it. And the kind of most obvious way that people do this, and is actually even still used and underlies a lot of the practical cryptography that's done today, is sort of the shared secret. So if I meet with Jason in advance and whisper into his ear, the password is, I'm not going to share this on the podcast. And then he, writes that down on a piece of paper. And then I apply some algorithm using that secret and to some data I have and send it to him. And then he knows in advance that secret and he undoes it. Then he can read. I can know that only he can read it. And we've shared that secret. We've shared that message. But we had to prearrange sharing that password. And that's tricky for a number of reasons. Because if we use the same password over and over and over again, we become at risk for people uncovering that by analyzing our data through various techniques. Also, it makes it difficult because in order to give him that password, I have to meet in person and securely deliver that. That's sort of expensive, especially if I need to do this with many, many people, or I want to do it with someone who maybe is in a place that's difficult to get to. But having a shared secret and using it over and over again, like we said, it leaves you subject to sort of someone analyzing patterns in what you're sending. And the solution to that it's still used today is sort of known as like the one-time pad. And this came from, I guess, one of the wars, World War I, World War II, where there would literally be sort of a pad of these shared secrets that two people would have. And the passwords, the things that you use to encoding were at very, very long, so that, you sort of were more immune to this analysis, and you only used it for sending one message. So if you sort of have a password that's as long as your message and you only use it once, it is actually very simple to prove that it's impossible for someone who doesn't have that password to decode your message, because every message of that length is equally possible.
Right. Like, to give you like a visual example of this, right? Let's say you have like one of these 10 code passwords, where it kind of looks like a telephone screen and you have the digits 0 through 9 and you have to punch in like, let's say a 4-digit password, right? So, you type in the password, let's say it's 1234 or something, right? So someone who's kind of watching you, maybe they sit right next to the door, they always see you kind of doing kind of the same motion. If they kind of see you enough times, they can kind of pick up on what's going on. Or maybe even a better way of making the analogy is someone can kind of dust the area and they can see, the 1, 2, 3, 4 buttons have like a lot of smudges on them. And maybe the 1 button is even more smudged because you got most of your finger oil on the 1 button. And so they can kind of like over time kind of reverse engineer the password, right? But if your password was like 30 digits long and you're punching, all 10 of the digits 3 times in just a random order, that's going to be really, really hard. Like it's not like they can't use the same tricks I just described, right?
So these one-time pads, these shared secrets, if you could sort of communicate them, they actually are sort of the goal of the goal of a lot of cryptography is to be able to sort of get to this, because this is really robust. And so what you end up with a lot of this is how to share those one-time pads. This is also, we didn't really say this, but the idea is you want people to kind of be able to know how you're encrypting your data, how you're applying your cryptographic techniques. So the algorithm that you're using to encode your data should be able to be known. And even if people know that, they still can't figure out what you're doing. That's like sort of because otherwise you run into all sorts of other problems, again, with this analysis. And in this particular one, these one-time pads are symmetric. So the thing that I do to my data, Jason also does to his data to undo what I did. And that's called symmetric key cryptography. So that's sort of, these one-time pads are both a shared secret and symmetric. So that begs the question, well, what are alternatives? And this is where you start to get to much more of what you hear today, which is public key cryptography. And public key cryptography means instead of making one key, I make 2 keys. One key that's public and one key that's private. And only I know my private key, but I can give away to the world my public key. And there's a lot of interesting things this unlocks. And it's sort of probably a little too difficult to explain the underlying algorithms of public key cryptography and the kind of how prime numbers are used as a part of this. I feel like that would get really confusing over podcasting. But when you hear words like RSA, cryptography, and then the pretty good privacy, the PGP set of tools also uses public key cryptography. And what it allows you to do is sort of a sequence of things. One is, if I have data and I want to make sure that only Jason can read my data, I look up in a telephone book of sorts, Jason Gauchi, his public key is, and whatever it is, and I apply the algorithm with his key to my data, and I now know that the only person who can undo that is Jason, because this is an asymmetric encryption. So in order to, if you apply the encryption key again, you don't get a decrypted data, you just get essentially garbled data. And so I apply his public key, I send it to Jason, Jason applies his private key, and then he can read my original plain text message, my unencrypted data. And so that solves, as me, the sender, as Patrick, the sender to Jason, I now know that only Jason can read my message. But when Jason receives the message, he doesn't actually yet know that Patrick sent it. So I can write in there at the end, dash Patrick. But if Bob, or I guess, if Bob sent that message and just wrote dash Patrick at the end, Jason has actually no way of being able to tell that apart. And this is another awesome thing that public key cryptography allows you to do, is what's called signing. And I'll see if I can get this correct and understandable. So when I go to sign a message, so I write my letter out, "Dear Jason, you're really awesome, dash Patrick." And then I apply his public, I get
every day.
Yes. I make sure to send you one every day because no one else is going to.
Oh, dang.
So I write that message. I apply his public key using the algorithm. I encrypt that data. Now I want to have him be able to verify that it's from me. So we talked about SHA-1 hashing before, and that's not secure, so don't use that. But assume you use some other kind of hashing that's secure.
Like SHA-5 or something.
Yeah. So and you take the hash. So some representation of the data that is reasonably easy to believe that no one else could sort of change the data in any way. You take that hash, and then now I do something a little bit weird. I take my private key and I apply using the same algorithm as before to encrypt the data. I encrypt the hash with my private key. Now I take the original message that's encrypted with Jason's public key, the hash which is encrypted with my private key, and I send those to not the encrypted data, the unencrypted data, and then my sign, and then I encrypt that whole thing because I don't want other people to be able to see that. So I want to encrypt the whole thing. I send the whole encrypted thing to Jason. Jason applies his private key to the whole message. So now he can see, Jason, you're awesome, dash Patrick. But he doesn't actually know it came from me yet. He has a bunch of sort of still encrypted data at the bottom. And he goes, oh, I want to make sure this came from Patrick. So he goes and looks up in the phone book of keys. He looks up Patrick, my public key, and he applies that to the encrypted data at the bottom of the message. He sees that now he has what he believes is a hash. So he hashes the decoded message that I sent him, and he compares that with the now unencrypted, hopefully, hash. And if they match, he knows that that message came from me, is only read by him, and nobody can have changed it. And that's sort of like the awesome part of public key cryptography. Or one of the many awesome things that allows you to do.
And that's basically, in a nutshell, how everything on the internet works. Like if you go on the internet this month and you pay your bills, the only reason you can do that is because of what Patrick just said.
Yep. So SSL encryption relies on this to be able to send your data securely. SSHing, if you SSH into your computer, also uses these techniques. This is very, very widely used.
Yep. Yeah, whenever you see that little lock icon on the browser on the top left, which now you should see almost everywhere, that means that this technique is in play. Like, it's just, I mean, it sounds complicated. I mean, and it is, but I mean, it's happening so fast that you don't even notice, but it's actually a lot going on. And it's every single packet is being encrypted in this way. So, I mean, this is happening, if you go to even just like google.com or something, this is happening thousands of times.
So
well, maybe not thousands, but hundreds.
Well, so yeah, what I just described, and I said these phone books, if you hear about sort of the certificate authorities that come up a lot recently in regards to SSL, those are about sort of the phone book of trusted companies. So that's where my browser can go to verify that a site I go to on Google is actually coming from Google. A site I go to from Amazon is actually from Amazon, is sort of these trusted places where those companies can put their public keys.
Right. I mean, there has to be at some point there has to be something to get it started, right? And the trust that gets the whole thing started, as Patrick said, are these stores. So like there's a whole bunch of work going into making sure that you get these public keys safely and securely.
And then the only other thing that I think is sort of interesting here, and then we'll move on from this part, is to say that these algorithms, these public key cryptography algorithms, are pretty slow. Like, they're not very efficient, both in the sort of generating keys is very expensive, but actually encoding messages this way is very costly. And so what you normally try to do is minimize the data you need to exchange this way. And then this goes back to the one-time pad we talked about before. So actually what you want to do is exchange in the encrypted something you've encrypted with one-time pads, but now I have a way to share my one-time pad with Jason. So I can use this public key stuff we just talked about to send him a one-time pad encryption, and then I can use that, which is very, very fast, to encrypt the rest of my data.
Yep.
But then every time Jason and I communicate, we exchange a one-time pad.
Right. Yep. Cool. So let's talk a little bit about the encryption. So you have a key, and let's assume we've sort of exchanged that key correctly and all of that. Now you have some data, like you have, every month I have a cron job that sends Patrick an email saying he's amazing because, I don't have time to do that.
I did mine personally, but yours is a cron job. I see where I lay in this stack.
And so I need to encrypt that somehow. Like, I need to take my key and take this plain text, and I need to apply the key and turn the plain text into something that looks unintelligible until it's decrypted, right? So, there's this idea of doing this has been around for an extremely long time. There's something called the Caesar cipher, which, correct me if I'm wrong, but it actually because it came from the days of Julius Caesar. I'm pretty sure that's actually accurate. And what it involves is basically applying a certain number. So the key in this case is just a number, like let's say 5, right? And what you do then is you take your message, which assume it's all letters, and you rotate all the letters by 5. So what that means is A becomes B, C, D, E. A becomes F, B becomes G, C becomes H, and it rolls over. So Z becomes E, right? Now, if the number was -5, you'd rotate in the other direction. If the number was 26, that would be a bad choice. You would not do any rotation, and the person would just see your plain text, right? A similar idea is a substitution cipher, which is a little bit more sophisticated. In this case, you're not doing that same rotation to every letter, but you use your key to generate a mapping. So you could say, A is G. So wherever I see an A in this encrypted or in an unencrypted text, wherever I see an A, I turn it into a G. And then now when I have the encrypted text, and whenever I see a G, because I have the key, which tells me sort of the mapping, I'll go back and change it back to an A, and I'll get my original message back. These ciphers are totally stateless, right? Like if you have the key, then you could just apply that key and you could decode half the message. You could decode the end of the message. It doesn't matter, right? But they're also extremely weak for this reason, right? Like, for example, if I have this huge message, let's say I encrypt like a huge document, right? I know that the word the is very common, THE, that word is very common in English. So if I see, in the encrypted message, if I see a bunch of 3-letter words, I could say, oh, that's probably the. So let me like apply my substitution cipher and let me see kind of how the rest of the document looks. And I can keep kind of playing around with sort of my innate knowledge of language and then end up with a substitution and end up like reverse engineering the cipher. So stateless ciphers are bad. And so people started making stateful ciphers. So for example, what I can do is I can say, I'm going to encrypt this block of data using my key, but then what comes out of the encryption is, the encrypted text, but then also some other numbers. And now when I go to encrypt the second block of data, I'm going to use those numbers. And even if the second block is exactly the same as the first, those numbers that came from the first block are going to make the second block look different, right? Think of it as like different inputs, right? And so now my trick that I just described where I find all the thes, that trick doesn't work anymore because the gets encrypted differently in the first block and the second. And so, everyone's kind of moved on to stateful ciphers, and there's the block-based approach I just described. And they have a way where you can actually do a streaming cipher. So you can, it doesn't have to be broken up into these chunks, and it can still take advantage of that sort of trick. Just as sort of trivia, that extra data that gets kept around from block to block, that's called the nonce. You can also start with a non-zero nonce, but you have to agree to it. So I could tell Patrick, hey, I'm going to start my nonce with 5. And then we both know the first block is going to have my key and then 5. And then the second block's going to be, different based on the content of the first block. And so most people use stateful ciphers, right? But the key thing here is if you want to do cryptography, like if you're building an app and you want to send something securely, and let's assume you're not using, SSH or HTTP, like you're writing your own custom thing. The answer here is use libsodium. So libsodium is an open source library. It was put together by, I think, like Google and Facebook and a bunch of companies. And that's it. Basically, libsodium has an encrypt and a decrypt function. They let you specify the nonce or leave it out. But use that library. Don't ever, ever, ever write your own cryptography library. Like, even if you look at the source code for AES or Salsa 20 and say, oh, I could write that myself. Don't do it because if you have a bug, it's going to end very badly, right? Like if you need something to be secure, then chances are there's consequences to it not being secure. Like maybe it hurts your business or your whole product is ruined or something, right? And it's just not worth taking that risk for no reason, right? Like libsodium is an amazing library. The API is very simple. It's constantly being peer reviewed. And when it gets to the nuts and bolts of it, just use libsodium. And that's pretty much it.
I think it's really easy to introduce, like we talked about all these steps. So Jason was talking about this stateful cipher where I was talking about exchanging one-time pads. But obviously you might want to send more data than the size of your password. And so you need to do all of this extra stuff to avoid these very, very clever and sophisticated attacks. And I think what Jason is pointing out is like, if you do this on your own, you're likely to sort of introduce some sort of bad assumption or a bug, a mistake, something you think or won't even know to check for. and someone sort of looking around and figuring this out could leave you very vulnerable. And so, yeah, I agree. Do not do this on your own, even if it seems really easy.
Libsodium has bindings for almost every language because everyone else is in the same boat. And there's really no reason to not use it.
Also, see the above talk about, things that have come out from WikiLeaks about why you don't want to be using something that could be vulnerable. And it's better for someone else to keep track of sort of the current best practices and help keep you secure.
Yep.
So one of the things that you also hear about cryptography, and we'll cover this, sort of at only at a high level, is all the stuff we've talked about works together to keep you secure. But very, very determined people with lots and lots of time on their hands still have a very good chance of being able to get at your data after some amount of time, right? The amount of time it takes, it's as kind of the equivalent as if you have some valuables in your house, some jewelry or whatever, and you put it in a safe. You don't want to sort of have a bank vault grade safe for what amounts to, a couple $1,000s in jewelry because you spend $1 million on a safe to protect $1,000. Doesn't make a lot of sense. Your jewelry isn't that valuable. And the cost of the safe is partly because of the size, but also sort of rated for how long it would take someone to break into that safe. And the thought is with enough time and money and dedication, someone will always be able to get into the safe. But hopefully, the stuff you're storing inside isn't worth that amount of effort, then it's sort of secure. And the same kind of applies for a lot of this encryption stuff. This is based on work that has to be done, and the work that has to be done to undo the encryption is much, much bigger than the work done to do the encryption when it's done carefully. And all of these techniques that we've talked about doing to try to make things better are about making sure that holds true, that the amount of work to decrypt is disproportionately larger than the amount of work to do the encryption. But if there turns out to be a problem in your algorithm or a problem in your data and that assumption breaks, now people can get at your data much more quickly. Also, as computers sort of become faster and faster, if you sort of, and this is where you hear like the number of bits of encryption, but the number of bits of encryption that were used, a decade ago, computers and GPUs and FPGAs and ASICs of today can break those much, much, much more quickly today. So it maybe takes an hour of computing time today to break what would have taken years before. And so what Jason was sort of alluding to before when he was talking about, what were you saying? Oh, it slipped my mind. You were saying something where
not to use your own crypto.
It's gone. Oh, well, Jason had a good point related to that before. But when you're setting how big these are, you want to sort of think about the best practices of today. But the thought is in, 100 years, who knows what's going to happen? And you don't know if your data is going to be secure. And one of the things people talk about that would cause a lot of problems in this assumption of it taking a long time to decrypt your data is quantum computers. And we don't have time to sort of go into the details of this, but the idea is that quantum computers can do the de-encryption calculations very, very quickly in parallel. And at some point, if quantum computers become, which not everyone agrees they ever will reach this, but if quantum computers became sophisticated enough, they would sort of be able to almost instantaneously decrypt the data that we use today because of their ability to, in parallel, run a lot of the math computations that are necessary to decrypt data. And so you'll hear people say this like, oh, quantum computers will sort of be able to undo this. And that's what they're sort of saying is quantum computers can do a bunch in parallel and they'll be able to decrypt these much more quickly. It is also
just to try to illustrate it as best I can. I mean, you could have a quantum computer that tries a bunch of different keys in parallel, and then returns the one that has the most instances of the word "the," and you could fire this off, and then the quantum processes that end up decrypting something with a lot of "thes" in it will start to bubble to the top, And using sort of this trick, you can try like 2 to the n keys in n time, and break almost any password. It's all kind of very pie in the sky theoretical stuff, but that's sort of the idea.
And then you'll also hear that typically immediately followed up with, but quantum computers will also make, hopefully for the first time, unbreakable encryption. And what people say there is there's sort of some interesting properties of the way quantum mechanics works that if things pan out, you'd be able to encrypt your data using these sort of quantum properties in a way that if someone ever tried to tamper with your data or use the wrong key, that the message would sort of self-destruct. So trying the wrong key on your quantum encrypted data, I'm being very loose with the words here, but like trying the wrong key against it would sort of make it explode if it wasn't right. And so you would never try unless you knew you had the right key because the data would just be destroyed otherwise. And it isn't like you can copy the data and try it again because of these quantum properties. You can't copy the data many, many times and just keep trying and destroying them until you find the right one. No, you're sort of guaranteed that that message only exists once and that can only attempt to be unlocked once.
Right, exactly. Yeah, you create sort of this entanglement, and when you make the copy, if you try a bad key on the copy, you'll destroy both copies at the same time because they're bound together. Yeah, so that's some pretty cool stuff that may come, in our lifetime, may not, we'll see. One thing that just as like a final takeaway is, if your client is compromised, you're hosed. Like if you get a virus on your laptop, you're done, dude. Like there is no cryptography that's going to help you. Like if you get a virus, that virus could just say, oh, I'm VeriSign now. And like all my public keys are this. And, oh, you thought you were going to capital1.com, but you're actually going to my website, right? Like, and so, one of the things that came out of the WikiLeaks was that they cracked like all of the end-to-end encryption, like WhatsApp and iMessage and all these things that have end-to-end encryption. The government was able to crack it. That's not true at all. Basically, all of those cryptography techniques are not cracked, but what they did is crack the client. Like if someone's typing a message to someone else and you've hacked their phone, you can just see what they're typing before the message is even sent, right?
So that data is kept in memory unencrypted. So either once it's been decrypted or before it's been encrypted, it's in memory in plain text, and they can just look at it there if they are able to run processes on your system.
Exactly. Yeah. So so cryptography will not help you at all if your system is compromised. And with that in mind, like if you have a virus or something on your computer, like don't even open your browser to find out how to remove it. Like use your phone or something, because anything can cause you to give all of your personal data at that point.
All right. Well, that was sort of a high level. Man, cryptography has a lot of parts. I don't even think we covered. There's tons of stuff I'm still thinking like, oh, we didn't cover this and we didn't cover that.
Yeah, I know. I mean, yeah, we could definitely talk about all the different algorithms but I think that we kind of gave everyone a high level, gave you all a high level. Definitely go on Wikipedia if you're interested. It's a fascinating subject. There's a lot to cover.
Yeah, I mean, I don't know, I guess in computer science you sort of are in and around in cryptography so much that you kind of bump up against it. You sort of read a little bit out, you sort of learn a little more, you go a little ways, you learn a little bit more. And I always sort of am fascinated, like I kind of want to deep dive into it, but I've never really had that opportunity. But over time, I guess, yeah, you just really build up a lot of sort of peripheral knowledge about it when working in computer science.
Yeah, I mean, I did my own. Actually, I didn't even do my own, but I used libgcrypt, which is an older library for Eternal Terminal. And basically, some security expert went to me and said, yeah, that library's not very secure, and so I should use libsodium instead. and here's a bunch of reasons why, which were unintelligible to me because I'm not from that field. But yeah, there's a wealth of information. I mean, I feel like it's one of those things that's like pretty far down on my list, because there's so many other things that I want to learn. But I could see, you know, if I got into it, I would definitely be just reading about it for days. I mean, there's just tons of amazing content, and it goes all the way back to like people encoding messages to help fight wars in the Roman Empire.
I think that's it. It feels like doing spy work. Like keeping secrets just sort of seems fun.
Yeah, totally.
All
cool.
right.
Well, that's the show for this month. Cryptography, I think, is fascinating. Actually, it came from a listener request. So thank you for that. Definitely keep emailing us with your ideas. You know, we keep all of them, and we get to all of them eventually. And you know, it's some of our best shows, especially now. You know, we've been doing this for a long time, and some of our best shows have come from users saying, "Hey, you know, I just blitzed through, you know, all 5 years of your show, and you didn't talk about this." So the person in particular, this was I won't say your last name, but this was Khan, who said, "Hey, check out. I noticed you didn't cover cryptography." Also, another gentleman by the name of Juan asked us the same thing, and because of you guys, you folks, we covered cryptography. So thank you for that.
All right. Till next time.
See you later.
The intro music is Axo by Binar Pilot. Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.